When we multiply radicals, we can multiply the radicands of the radicals and simplify. In this case, we have the square root of 6x times the square root of 8x. If I multiply the radicands 6x and 8x, I get 48x squared. And then I can simplify that by one of our methods of simplifying radicals. In this case, I will expand this in a prime factorization. And noticing, since I have the square root, I can take out a pair of 2's as a single 2. I can take out another pair of 2's as a single 2. And I can take out a pair of x's as a single x. And this radical simplifies down to 2 times 2 times x times the square root of 3 still left inside, or 4x root 3. This can also be done for radicals that may have been simplified already, something like this: 2 times the square root of 3x times 4 times the square root of 6x, in which now we have a coefficient in front of each one of the radicals. In this case, we still can multiply the radicands, or the numbers inside the radicals, but we also can multiply the numbers on the outside. We cannot, however, multiply a value on the outside of a radical times a value on the inside of the radical. So I could not multiply 2 times the 6x. If I multiply the values out front, 2 times 4 to get 8. And if I multiply the radicands, 3x and 6x, to get 18x squared, I can then simplify the radical by whatever means I want. In this case, I will use the method in which I break down the 18 into a perfect square of 9 times 2. X squared is a perfect square, so I can put it in the radical containing perfect squares and then simplify. So those are some examples of simplifying expressions involving multiplication of radicals. Let me give you a few practice problems. Here's the first practice problem. Pause the video, work the problem, and come back to check your answer. In this problem, if I multiply the radicands, 20 times 6 would give me 120 inside the radical. X squared times x would give me x cubed, and y times y would give me y squared. Let me expand this 120 into prime factorization. And because we're taking the square root, I can take out a pair of 2's as a single 2. I can take out a pair of x's as a single x, take out a pair of y's as a single y, and on the inside I'm left with 30x. And one more example, or one more practice problem. Work the problem, or pause the video, work the problem, and then come back to check your answer. In this example, I can multiply the coefficients out front, 6xy. On the inside, I can multiply the radicands, 150xy squared. If I simplify the radical, in this case, I will break it into a perfect square times whatever is needed to multiply to give me this value up here. 150, I can take out 25 as a perfect square, times 6. I can take out a y squared as a perfect square, and x is left in the other radical. If I simplify this radical, I get 5y. And multiplying all these values out front, I have 30xy squared times the square root of 6x. So that's how we can handle multiplication. Multiplying values in front of the radicals together, multiplying values inside the radicals together, and then simplifying the radicals. For division, we can use a method called rationalizing the denominator, which means that we want to change this irrational number of the square root of 3 into a rational number. To do that, I can multiply the numerator and denominator of my fraction by some value that will give me a perfect square in the denominator. In this case, the square root of 3 times the square root of 3 would give me the square root of 9, which is a perfect square in the denominator. If I simplify this radical, I have a value of 2 root 3. Now notice that I've multiplied by root 3 over root 3, which is multiplying the fraction by 1, which means I'm not changing the value of the fraction, just changing the looks of the fraction. And that's how we can take care of division. Another example, 8 over root 18, I could multiply the top and bottom of this by the square root of 18, but that's a pretty large number when I get to multiplying, so I could multiply by something smaller, for example the square root of 2, which would still be a value that will give me a perfect square in the denominator. So if I multiply my numerator and multiplying the denominator, I get the square root of 36, and if I simplify, we have a perfect square in the denominator, so it came out to be a rational number. If I simplify, I get 4 root 2 all over 3. Also, when I simplify, I can only divide down values that are both inside or both outside of a radical. So here I can divide the 8 and the 6 down, divide them both by 2. We also may have a fraction involving some expression in the denominator. Expression containing more than one term. So in this case, I want to rationalize the denominator. I want to get rid of the square root, the irrational number, from the denominator. So I want to multiply the numerator and denominator both by the same thing, so I'm multiplying by 1, and I want to multiply by the conjugate of the denominator, the conjugate being the exact same terms except with a different sign between. Here I have 5 plus root 3, the conjugate is 5 minus root 3. If I multiply this out in the numerator, 20 minus 4 root 3. In the denominator, if I expand this out, 5 times 5 is 25. 5 times negative root 3 is minus 5 root 3. Root 3 times 5 is positive 5 root 3. And positive root 3 times negative root 3 is negative root 9. In the denominator, when we multiply conjugates, the middle terms are always opposites of each other, so they'll just subtract out. And I'm left with 25 minus the square root of 9, which is 3. And notice that that is a rational number. Remember, we're trying to rationalize the denominator, get rid of the square roots. Now we have a rational number in the denominator, so we've done that. If I want to simplify this fraction, I can divide each of these terms in the numerator and the term in the denominator by 2. (10 minus 2 root 3 all over 11), or I could break it into separate fractions. 10 elevenths minus 2 root 3 all over 11. Let me give you a few practice problems. Try try this problem. (12 over the square root of 8). Pause the video, work the problem, and come back to check your answer. In this problem, I could multiply the top and bottom by the square root of 8 if I wanted to, or I may notice that the square root of 2 will give me a perfect square in the denominator. If I multiply this out, 12 root 2 over the square root of 16. Square root of 16 is a perfect square. If I simplify by dividing the 12 and 4 both by 4, I get 3 root 2. If you had multiplied the top and bottom by the square root of 8, you still would have gotten this answer. It just would have taken a little more time at the end to simplify. Another example, 4 minus 3 root 2 over 4 plus 2 root 2. Try this problem and then come back to the video when you want to check your answer. If we want to rationalize the denominator, we can multiply the numerator and denominator by the conjugate of the denominator. Since the denominator is 4 plus 2 root 2, I can multiply the numerator and denominator by 4 minus 2 root 2. If I expand the numerator, 4 times 4 is 16. 4 times negative 2 root 2 is negative 8 root 2. Negative 3 root 2 times 4 is negative 12 root 2. And negative 3 root 2 times negative 2 root 2 is positive 6 root 4. In the denominator, 4 times 4 is 16. 4 times negative 2 root 2 is negative 8 root 2. 2 root 2 times 4 is positive 8 root 2. And 2 root 2 times negative 2 root 2 is negative 4 root 4. If I simplify, in the numerator, I can combine these like radicals to give negative 20 root 2. The last term plus 6 times 2, simplifying the square root of 4. In the denominator, the middle terms cancel out. The last term is 4 times 2. If I simplify further, I have 16 plus 6 times 2, which is 12, so I have 28 minus 20 root 2. And in the denominator, 16 minus 8, which is 8. I can divide each of the terms in the numerator and the denominator by 4, giving me 7 minus 5 root 2 all over 2. Once again, when we're dividing radicals, we use the method of rationalizing the denominator, which means remove the square root from the denominator, the imperfect square root, making everything perfect squares. We do that by multiplying by the conjugate of the denominator.